Hey guys, in this video we're going to be talking about a problem involving rotations, and we're then going to use that to prove the trigonometric angle sum formulas, as well as proving a nice fact about complex numbers. So let's get into it. Here we have a point P with coordinates x and y. X and y are both known to us. That point P is then rotated about the origin, and in orange it's rotated anticlockwise by an angle of theta, and this new point will be P tilde. And the problem is to find the coordinates of P tilde in terms of x and y and theta. So let's get into it. To solve this problem, we're going to need to use some facts about the unit circle and trigonometry. So I'm going to, over here, draw up the axes and the unit circle. So the unit circle will be in yellow, and keep in mind that it has a radius of 1. Then, let's say I have a point, which we'll call P, that lies on the unit circle, and it makes an angle theta with the x-axis as shown. Now, cosine of theta is defined to be the horizontal coordinate of P. That's the definition of cosine theta. And sine theta is defined to be the vertical coordinate of P. So we can write P as cosine theta and sine theta. So many of you may be familiar with the triangle definition of cosine theta and sine theta. So I'll show how the triangle definition is indeed consistent with the unit circle definition. So over here, I've drawn P in the second quadrant because I'm emphasizing the fact that this is true for any value of theta, which means, of course, cosine theta and sine theta can be negative or positive. But now I'm going to draw P so that it's in the first quadrant, so I can show why this is true for triangles, or why it's consistent with the triangle definition. So that's going to be our point P. And I'll draw the sides of the triangle in blue, and this is going to be an angle theta. Now, since we're on the unit circle, the length of the hypotenuse will be 1. And since cosine theta and sine theta are positive, and lengths are always positive, the horizontal length will be cosine of theta, and the vertical length will be sine of theta. But now notice, in our right angle triangle, we have adjacent over hypotenuse is equal to cosine theta over 1, which is just cosine theta. But we all know that in a right angle triangle, cos theta is adjacent over hypotenuse, which means this is consistent. This is consistent with our triangle definition. Similarly, if we have opposite over hypotenuse, this is going to be sine over 1, which is sine theta. And this is also consistent with our triangle definition, because the triangle definition says that the opposite over the hypotenuse is sine of theta. So this means that the unit circle definition is consistent with the triangle definition for small values of theta in the first quadrant, and the unit circle definition is actually an extension of the triangle definition. So now we're going to do some more unit circle stuff. So I'll drop the axes again. We have the y-axis and the x-axis, and I'll put in the unit circle in yellow. So now we have this point over here, which is 0, 1, and it has been rotated by an angle of theta. It's been rotated by an angle of theta to get to R, and we want to find the coordinates of R. So there's two ways of doing this. There's our way 1. Way 1 is to note that this angle over here is a right angle, and that's going to be pi on 2, which means that this whole angle over here is just going to be theta plus pi on 2. Therefore, we have r as cos of theta plus pi on 2 and sine of theta plus pi on 2. Because remember from before, cos theta is the horizontal component and sine theta is the vertical coordinate, I should say. And in this case, instead of having this angle theta, we have our angle is theta plus pi on 2. So here we have the horizontal coordinate, the x coordinate, and the vertical coordinate, the y coordinate. But there's actually going to be another way to do this problem, which is going to help us to solve our rotation problem. So what I'm going to do over here is I'm simply going to redraw the coordinate axes. I don't have to do this, but I'm doing it simply to illuminate the problem better. So I'm simply redrawing it. I'm not changing any of the mathematics at all. So this will be our point R over here. This will be theta, and that's going to be our right angle, not that we'll be using it. So now I'll introduce a concept. Consider we have just this point over here. I'll just call it like Q or something. So at Q, y equals 0 and x equals, say, minus 1.2. Then if when we put this on our rotated graph, Q is going to be up here and y is still going to be 0 and x will still be minus 1.2. But if x is minus 1.2, then minus x equals 1.2. So you're thinking, okay, why did I do that? That tells us nothing. But there's actually a nice geometric interpretation. This isn't just an algebraic statement. There's a geometric meaning behind this. So if this is the x-axis, you can kind of think of this up here as the minus x-axis. So if minus x equals 1.2, like yes, that's minus 1.2 along the x direction, but you can also think it as 1.2 along the negative x direction. So this is one step in the negative x direction, and that's that extra 0.2 of a step in the negative x direction. And if we think about it like this, with this minus x-axis, that's actually going to help us think about our problem and help us find the coordinates of r. So let's recall this. Remember, cosine theta is a horizontal component and sine theta is the vertical component. But hang on, this looks quite similar to what we have up here. We have the horizontal component is going to be cos theta. But look, our horizontal axis in this case is represented by y. So we have y equals cos theta. And the vertical will be sine theta. But look, the vertical axis is represented by the variable negative x in this case. So have sine theta being negative x. So if we kind of convert this back into our normal way of thinking, we have r as our minus sine theta and cos theta. So this is, remember, just normal notation x and y. But hang on. Didn't we say that r is cos theta plus pi on 2 and sine theta plus pi on 2? But this is the same r. These are the same points. And if the points are the same, then the coordinates should be the same. So that means the x coordinates must be equal and the y coordinates must be equal. So that means we can say that sine of theta plus pi on 2 is cos of theta, because we're equating the y coordinates. And we can say that cos of theta plus pi on 2 equals negative sine of theta, because we're equating the x coordinates. And of course, I could have shown this through the angle sum formula, but that would be a bit pointless for me because I'm actually going to prove the angle sum formula. So the lesson here, just take this away. We'll use this fact later in our proof. That was the purpose of all of that. So now we have the solution. We have the solution to the problem I mentioned before. So I'll redraw it here. This is y-axis, that's x-axis. This will be the point P with coordinates x and y, which are known. Now I'll draw the kind of x. I'll draw a rectangle here, and I'll put the x coordinates in red and the y coordinates in yellow. I should say the y sides in yellow anyway. So this point over here, we'll just call this point A, and it will have coordinates x and 0. And this point over here we'll call B, and this will have coordinates 0 and y. So now I'm going to rotate this rectangle. And I'll just make it a bit easier to see which rectangle is which. And then I'll erase that. Make it nice and neat. So here's our rotated rectangle. And as before, this angle is going to be theta. But since in a this angle is going to be equal to that angle because we're just rotating it, we're not changing anything. So this angle is also going to be theta between the reds, and the angle between the yellows again will be theta. So I'll label these points on the new rectangle. This one will be P tilde because it's the rotation of P. This one will be A tilde as it's the rotation of A. And this one will be B tilde as it's the rotation of B. So we're going to use all of our unit circle facts we did before to find the coordinates of A tilde and B tilde, and then we can use that to find the coordinates of P tilde, and that's going to be the coordinates of our rotated point. So we'll start with A tilde. So I'll redraw this. That's going to be A, and that's going to be A tilde, and here we have an angle of theta. So this is very similar to the situation we have before, but you've got to remember that this circle, it isn't quite the unit circle. This circle has radius x, because look, this distance over here is x. So our radius of the circle will be x. So the coordinates of A tilde won't be cosine theta and sine theta, because we've scaled everything up by a factor of x. So that means the coordinates of A tilde will be x times cosine theta and x times sine theta. And then we can do something similar with B, the coordinates of, B tilde. Now keep in mind that B will line the circle with radius y, and as before we have theta here, and that's pi on 2, so the whole angle is pi on 2 plus theta. So the coordinates of B tilde will be y times cos of theta plus pi on 2, and y times sine of theta plus pi on 2. So I've got the coordinates of A tilde and B tilde, and we can now use this to find P tilde. So how would we get that? One way would say we could start at B tilde, we could go across over here and up over there. But how much, if we knew how much to go across from B tilde and how much to go up from B tilde, then we could find P tilde. However, those kind of blue steps there are going to be the exact same as the steps that get us from the origin to A tilde. And this is true because the opposite sides of a rectangle are going to be parallel to each other and equal to each other in length. So really, this is just the same triangle that's shifted, which means these are going to be the same. So that one's going to be our x step, and that one's going to be our y step. So we have the x step. Well, the x step is just going to be the x coordinate of A tilde, which is this thing, x cos theta. And notice that our x step has already got the negative sign built into it, because in this case, theta equals maybe like 3 pi on 4, and cosine of 3 pi on 4 is negative. So we don't have to flip any of the signs because the arrows are in different, going left versus right or up versus down. It's already got all of that taken care of. So then the y step is just going to be x sine theta, which is the y coordinate of a tilde, x sine theta. But that means we can add these coordinates onto b tilde to get p tilde. So I write the x coordinate of p tilde. This is going to be our x coordinate of b tilde, which is going to get us to there, and then we'll add on this x step to get us to there. So that's going to be y cos theta plus pi on 2 plus our x step, which is x cos theta. And similarly, the y coord of p is going to be the y coordinate of b, which is y sine theta plus pi on 2. And then we'll add on our y step, which is going to bring us up there, plus x sine theta. And now we can use our fact from over here that we proved earlier to kind of simplify this. So that's going to be x cos theta minus y sine theta. And this is going to be x sine theta plus y cos theta. So there we go. These are the x coordinates of p tilde. So I'll just sum this up all in one statement. Therefore, x comma y just goes to x cos theta minus y sine theta, and x sine theta plus y cos theta when rotating by theta anti-clockwise. So there we go. That's the coordinates of our rotated point. Now, we're going to do two things with this formula. We're going to use it to prove the angle sum formulas in trigonometry, and we'll also prove a fact about complex numbers. So, corollary 1, angle sum. Hey, that rhymes. So here we're going to let x equal cos of alpha and y equal sine of alpha. So note that x and y will in fact lie on the unit circle. So x and y are the coordinates of p. And since it lies on the unit circle like this angle is going to be alpha. And then we're going to rotate this by an angle of theta to get our new point, p tilde. So the first thing to note is that, do this in what color? White. The first thing to note is this whole angle here is just alpha plus theta. So we can write p tilde as cos of alpha plus theta and sine of alpha plus theta. Because p lies on the unit circle, and this is just a whole angle of alpha plus theta. But we can also use this fact over here to find p. So we can also say p tilde is, so we're going to sub cos alpha into the x's and sine alpha into the y's. That's going to be cos alpha cos theta minus sine alpha sine theta, and sine alpha cos theta plus cos alpha sine theta. But hang on, these are the same point, so their coordinates must be the same. So clearly, we have cos of alpha plus theta equals cos alpha cos theta minus sine alpha sine theta. And we have the sine of alpha plus theta is sine alpha cos theta plus cos alpha sine theta. So there we go. That's a proof of the double angle formulas using all this unit circle stuff. So then I'll do corollary 2, complex numbers, and I'll just move this down so we can look at it Just so we can use this for reference. I'll just shrink it. Not too much. There we go. So suppose we have so I'm going to draw the Argand space diagram. It's a horrible axis. There we go. So that's going to be the imaginary axis, and that's going to be the real axis. And I'll draw a point, or a vector, if you will, z, which is x plus I, y. So z times cos I sine theta is x plus I, y times cos theta plus I sine theta. Because cos I sine theta is just means this, and z is x plus I, y. And then expanding these brackets, we have x cos theta plus I x sine theta plus I y cos theta plus I squared y sine theta. But remember, I squared equals -1. So this is just going to be a minus y sine theta. So now we can collect the real and imaginary parts. So I'll do the real parts in red. And I'll put the imaginary parts in yellow. This means that the our new point, which might just be over here, which is z times cos I sine theta, the horizontal coordinate, of z cos I sine theta is just going to be the real part, because real represents a horizontal axis, and the vertical component is just going to be the imaginary part, since imaginary represents the vertical axis. But hang on, this is exactly what we have over here, x cos theta minus y sine theta, x cos theta minus y sine theta, x sine theta plus y cos theta, and x sine theta plus y cos theta, which means, therefore, geometrically, this is a rotation, just like before. So in fact, when you have a complex number z and you multiply it by cos I sine theta, this is equivalent to simply rotating it by theta. So those are the same lengths, and rotating it by theta. So there we go. That's why multiplying a complex number by cos I sine theta gives a rotation. So I hope you enjoyed the video. Make sure to turn on notifications, comment, subscribe, smash that mother function like button. Peace.